Let's try our first example on the top of page 78. The velocity of a particle can be modeled by v of t, where v is measured in meters per second and its position at time t equals 0 is 5. And we're given the graph of v. So I'm going to label this so that I remember what graph I'm working with. Okay, we're first asked to evaluate the definite integral of v from 0 to 7 and explain using correct units what this represents. So we know that in order to do that, we need to know the area between the curve and the x-axis. So we can do that geometrically. So this first shape, I've got a triangle, 2 times 2 times 1/2. We get an area of 2. I'm going to break this up into smaller shapes. So we've got an area of 2 there, an area of 4, 1 times 2 times 1/2, that gives us an area of 1. I'm just going to go ahead and do the whole graph. We've got another triangle with an area of 1 and then an area of 2. Okay, so if we evaluate, since we're going from left to right, I know my area above the axis is positive, below is negative. So we have 2 plus negative 2 plus, I'm going to combine the 4 and the 1, negative 5. And so we're adding the areas from where x equals 2 to where x equals 7. So we stop there. And we get a negative 5 when we combine those. So to explain what that represents in the context of the situation, remember we're talking about something that happened over an interval. And since we're talking about velocity, really what we're learning about is the change in position. So if I'm going to use s to represent position, if the derivative of position is velocity, then that really means that s is the antiderivative of velocity. And we'll talk more about the antiderivative in our next unit. So when we integrate v over 0 to 7, we're learning about the function that came before v, its antiderivative position. So between t equals 0 and t equals 7 seconds, so we need to include our units, so we could either say displacement, or we could say, we could talk about how the position has changed, but that's what displacement is. So between t equals 0 and t equals 7 seconds, the displacement of the particle is negative 5 meters. So a few other ways you could say that is you could say the position between t equals 0 and t equals 7 seconds, the position of the particle decreases by 5 meters, or you could say the particle changes, its position changes by negative 5 meters. I think displacement's the best way to describe that change. All right, in part B, what is the acceleration of the particle at time t equals 3? So remember that the derivative of velocity is acceleration, and we have to show that relationship in our FRQ response. Is the speed of the particle increasing or decreasing at time t equals 3? Okay, so let's first find the acceleration at 3. And the only way to find the acceleration at 3 is really for us to know the derivative of the velocity at 3. So since we have a straight line here for velocity, the slope of that line is going to be my derivative. So I just need to know the slope of this line segment from 0 to 4. So if I just look or pick 2 good points, I'm going down to the right 2. So the slope of that line segment is negative 1. So since since the derivative is the slope of our tangent line, and when we take the derivative of something that is linear, it's just the slope of that line, we get that v prime of 3 is negative 1. So our acceleration is -1 meters per second squared. So we're asked if the speed of the particle is increasing or decreasing. So the velocity at 3 is also negative. We could actually calculate it, but that doesn't really matter. It just matters that we know that the velocity is negative. The acceleration is also negative. So the speed of the particle is increasing. And remember, the speed of a particle or an object is increasing when velocity and acceleration have the same sign. So I'm going to say because both v of 3 and a of 3 are less than 0. Okay, in part C, is the particle moving left or right at time t equals 8? So remember that this again goes back to our velocity. So our velocity at 8 is, it looks like 2. All that really matters is that we know that it's positive. So at t equals 8 seconds, the particle is moving in the positive direction. So the particle is moving to the right. And the reason for that is because v of 8 is greater than 0, or v of 8 is positive. Okay, so for part D, now we're getting to this idea of an accumulation of change. So we're asked, what is the position of the particle at time t equals 5? Well, we have to know some position, like we have to be given some initial position so that we could write an accumulation function. So we are told in the prompt that the position of the particle at time t equals 0 is 5. And somewhere, I think I used the letter S on here somewhere, just at the top. So I'm going to use S to describe position. Sometimes we use X, sometimes we use S, it doesn't really matter. So S will be the position of the particle. So now this information, I could write an equation and say that S of 0 is 5. So the position at time t equals 0 is 5 meters. So if I know that down here, that S of 0 is 5, I could write an accumulation function that's going to give me the position of the particle for any time t. And I'm going to need that for part E, so I might as well write it in part D. So for any time t, we have this initial known position. It doesn't have to be at t equals 0, but this one is. And from there, we could add the definite integral from 0 to t, where t will represent any time. And what we're integrating is the derivative of s, which is v. Now, when we write an accumulation function, the variable of the function is t, but we need a dummy variable in the function itself. So I'm just going to say v of x, d of x. It doesn't matter what variable you use there, as long as they're the same. It's just standing in for what we'll replace with t. So this accumulation function will tell us the position of the particle at any time t. So now if I want to know the position at t equals 5, I just substitute in a 5. As soon as I replace that t with the number 5, I could rewrite this as v of t, d of t. Okay, so we said that s of 0 is 5. So I can substitute that for s of 0. I now need to go back up to my graph and calculate the definite integral of v between 0 and 5. So that's, let's see, we wrote that as a 4, but really that's a 2 and a 2. So we've got a positive 2 and a negative 4. And so that's what, 7 minus 4. Let me double check that. Okay, so I'm double checking what I think I wrote on my paper is incorrect. So we said that, okay, so at S of 0, we're at 5. We're going to add this 2, subtract this 2, and then subtract that remaining 2. Okay, so this is correct. So we should be at -7. Nope, 3. Wow. I don't know, it's adding the 7. Sorry, 7 plus -4 is 3, not -7. So we should be at 3 meters. So the position of the particle at t equals 5 seconds is 3 meters. So again, that's our initial position of 5, and then we add to that the change in the position between 0 and 5. All right, then part E, when is the particle furthest to the left? So this is really asking us, what is the absolute minimum position? So we need to treat this like an absolute min, absolute max question. And if I'm finding the absolute minimum value of S, I need to consider its critical values and its in the endpoints of the domain of the interval I'm looking at. So to get the critical values, I need to make a connection between S prime and V if I have not already. So the derivative of S is V. So for the critical values, I'm really looking for where V equals 0. So if I go back up to my graph, V equals 0 at 2, at 7, and at 10. So that's going to happen when t equals 2, 7, and 10. And I'm asked about this over the interval 0 to 10 since it doesn't specify, but that's the interval that I have. So when we go ahead to make our table, in my table, I'm going to put values of t. So 0 being the endpoint of the interval, 2, 7, and then 10 is both a critical value and the other endpoint. And then what I want is to find values of S because we're looking for the absolute minimum value of S. So the accumulation function that we wrote up at the top in part D, we're going to use that in part E to fill out our table. So we already know from the given information that S of 0 is 5. So to find S of 2, I know that's going to be S of 0 plus the accumulation of change from 0 to 2 of V. So if I go up here from 0 to 2, I'm adding a positive 2 to that. So that is 5 plus 2, which is 7. All right, for the 7, so S of 7 is again our initial position plus the accumulation of change from 0 to 7 of V. Now, you really could start at 2 since we know S of 2 is 7 and just add the change from 2 to 7. Either way works, but we need to show our work for this in one way or another. So if I do it this way, this is 5 plus, and then from 0 to 7, the first 2 and the 2 that's beneath the axis cancel out then because it's negative, and then I have a negative 5. So my accumulation of change is a negative 5, and when I add that to my initial 5, I'm at 0. So then lastly, to find S of 10, we can go back to our accumulation function, or we could just start with the 0. So for S of 10, we could start with S of 7 instead of S of 0, and add to that, the change from 7 to 10 of V. So it's like we've written a new accumulation function if we do that. So the change from 7 to 10 is a positive 3. That's the area between the x-axis and the curve. So I'm adding 0 plus 3. That gives me 3. Okay, so when is the particle furthest to the left? Well, it's furthest to the left when t equals 7. So we just need to write that somewhere to answer the question. Okay, t equals 7 seconds. All right, this last part, we were asked to evaluate the definite integral of the absolute value of v over 0 to 10. So if I think about that, the absolute value of v is really just like if I take all my v values and make them positive. So for example, v of 4 is -2, but for the absolute value of v, it would be +2. So really my graph would be up here. V of 6 is -2, but for the absolute value, again, it would be positive. And then we would see this. So basically, the absolute value of v is going to take anything that is negative below the x-axis and flip it up above the x-axis. So this trapezoid that has an area of, 7 below the axis is now above the x-axis when we consider the absolute value of v. So it's everything above. So we don't have to resketch the graph. We just, when we add those areas, we just have to make sure we consider them all positive. So from 0 to 10, we're integrating the absolute value of the function v over that interval. So we're going to add all the positive areas, so to a +7 for all that area that's below the axis, and then a +3. So 2 plus 7 plus 3, so that gives us a +12. And our units are meters. So then explain what this represents in the context of the situation. So remember, when we talk about absolute value, this is not the displacement, but this is the total distance traveled. So like if you are at your home and you go to the bank, and the bank is 1 mile away, and then you come back, well, your displacement is 0 because you're back where you started, but your total distance traveled is 2 miles because you drove a mile to the bank and a mile back. So we need to keep that in mind when we answer these questions. Okay, so the total, or actually I'm going to start it with the time intervals. So between t equals 0 and t equals 10, what is this, seconds? The total distance the particle travels is 12 meters.